Hi. So, it's exciting to begin this last chapter, especially because I love this topic so much. And unfortunately, we don't get to go super in depth with it, but we do get to touch it lightly. And I think it's the most valuable that you'll take away. I feel like everything we've learned, every chapter prior, all led to this moment of being able to take as many samples as we need and just do hypothesis testing on as many as we need and as many populations as we want to compare. So, if we wanted to compare, let's just say, if we had three different populations, let's say, of students, right? We had adult students and freshman students out of high school, and then maybe another group, let's say working full-time students, something like that. I don't know. And then we wanted to compare their GPAs from when they took certain math class, right? And to see if one group is disadvantaged, like the average GPA for adults versus incoming freshmen versus 40-hour working student, are they different, right? Can we actually say that we're disadvantaging one population over the other? Well, in order to make that claim and it be supported, we would have to do what we call an ANOVA, one-way variance analysis. And that means we can compare more than two populations. So we would have like the incoming freshmen, adults, and 40-hour working students and compare their GPAs and say, no, there is no difference, status quo, the null hypothesis, or at least one of these are different. And if there's enough evidence to support that alternative, at least one of those averages are different, then yeah, we are disadvantaging one population of students. And this is how we make our decisions that we do in education. We constantly do these type of ANOVA tests. So because it's a larger type of sampling, right, we're having more than two samples. We also have a different distribution. So notice we've had so many different distributions in this class, and I promise this is the last one. But the last one that was different was the chi-square distribution, remember? And then we had this, now we're going to have this distribution. We also had the one prior was the linear regression distribution testing the significance of the correlation coefficient. And so now we have what we call the F distribution. So let's go ahead and just talk about a little bit about what ANOVA is, the one-way variance analysis, and the F distribution. So So the one-way ANOVA, the analysis of variance, is an inferential method used to test the equality of three or more population means. In other words, in ANOVA, the null hypothesis always means that the mean of the different populations are equal, and the alternative is at least one is different. So just to give a little graphical idea, right, we have this bell curve, right? And what we're saying is, here's the null. The null is saying that the first mean is equal to the second mean is equal to the third mean, right? So this would be like H sub 0, where we assume status quo, that there is no difference between the population. And the alternative would be where we have this initial mean, let me put it in black, here. But then either maybe the second population could have this curve. Oh, this is a terrible curve, but its mean and peak over here. Or we could have, a combination where the first two are okay, and then we have a peak over here with the third, meaning any one of them could be different from the other, and that would be the alternative. So it's similar to when we did like goodness of fit, or independence, like that whole chapter 11 chi-square distribution, right? It was either like it was a good fit or it's not. the variables are independent or they're not, right? So this is the same thing here. Either there is no difference between the means or at least one is different. And that's pretty much what ANOVA is. So, okay. So one thing is that this is just a warning because this could get really involved, right? So some students say, well, if one of them is different, we could end up conducting a lot of different tests, right? So for example, if we assume that they're all the same on the null, then we could say the alternative is like a variation, right? You're saying, oh, well, this means that mu sub 1 could be equal to mu sub 2, but not mu sub 3. Or mu sub 1 could not be equal to mu sub 2, but these two are equal. Right? And then we could have where, oh, okay, well, mu sub 1, they could all just be different from each other. And so what we end up getting is like all these different combinations and permutations of how it could be different. This is warning you, do not do 3 different hypothesis tests. Do not do combination after or permutation after permutation. Like all we should be saying is that at least one is different. Because if we do at least one is different, we can just do the ANOVA test and it does kind of all that work for us of all those combinations, right? So what are some requirements to perform a one-way ANOVA? Okay, there must be k simple random samples, right? So they have to come from populations. So those means, those criteria for means that we had in prior with 2 means and 1 mean where the sample size should be larger than 30 and samples should be independent and the data should come from approximately normal distribution, that's going to be the criteria here as well for each population, just like we did back when we compared 2 population means. And so the other piece of information that's new to us is that the population variances must have the same variance. Okay, and the factor is a categorical variable, and we'll talk about the factor in just in a moment, and then the response is numerical.